So today we start chapter 3. Chapter 3 is about elements and compounds. These are the little particles that make up all matter, okay? An element and a compound are pure substances. Their composition is always the same. And here you're showing a picture of a statue that's made out of pure gold. Imagine how much money you could get for that, okay? So an element is the fundamental substance, and it cannot be broken down by any simpler substances. That's it. That's as small as you get. And if you want to know what an element is, periodic table, there'll be one that you can download, and I suggest you do that so that you have it with you so you can scribble and do all that good stuff on it. Because the periodic table has all the elements and we use it for a lot of things. Okay, there's 118 known elements, and all but 4 of the first 92 occur naturally. When they don't occur naturally, that means they were made in a lab. They were looking at radioactive materials, things like that. A lot of the elements on the very bottom, those last bottom 2 rows, those are radioactive and those are called man-made. Not all of them are. I think 2 of them are, uranium and plutonium. But man-made elements there's some of those as well. Okay, so all elements beyond 92 except for plutonium are man-made. Okay, so again, you'll see that. That there are some man-made elements. They are created in a lab when they're doing stuff to elements. Okay, an atom is the smallest particle. So here we have a copper penny, and you can see, if we had a really nice microscope, you could see the particles and how they would be all lined up to make these solids. Okay, here's examples of some of them. If you're looking at percentages wise, we're looking at the mass of the most abundant elements in the Earth's crust, the oceans, and the atmosphere. Number 1 is oxygen, almost half. Okay, and a good part of that is because a lot of our world is water. Water is H2O. You got that oxygen there. We got silicon, aluminum, iron, calcium, sodium. You can see, all of the particles, or all the elements, excuse me, that you'll find in our world. But you can see that these elements make up, 99.51% of everything. So a lot of the elements, there's very, very, very little of them. Okay. So the most abundant element in the Earth's crust, oceans, and atmosphere, if you remember, was oxygen. Okay. And again, it's saying element. Yes, it would be water, but that's not an element. That's a compound. Okay. Here we're talking about in our bodies. And again, oxygen, 65%, because again, it's part of water, and 70% of our bodies are made out of water. So oxygen, weight-wise, makes up a lot more water. It's 16 grams out of 18, so it's quite a bit. If you go by percent mass, most of water is oxygen. Okay, so you can see oxygen, carbon, hydrogen, nitrogen. These are the big 4. Okay, and then we have little bits of calcium, phosphorus, magnesium, potassium, sulfur, and sodium. Okay, so we're mostly oxygen, carbon, hydrogen, and nitrogen. Okay, all right, so when we're talking about the names of elements, some of them make perfect sense to me, like carbon, its symbol is C, okay. And their names come from, a lot of times, the people that discovered them, they give them a name. Okay, like here we have iodine. It has a violet-like color. Iodine, it's especially when it changes from a solid to a gas. And so it got the Greek name idos. Okay, so that's where iodine comes from. There's bismuth. This is a white mass of, it's a metalloid. And again, it came from a German name. We have germanium, named for Germany. And if you look on the bottom ones, especially the newer elements, the higher numbers, you'll see there's Einsteinium, Mendelevium, Berkelium. They were named for either places where they were discovered, or somebody got an element named after them, stuff like that. Okay. Now, when you're using the symbols, some of them make such perfect, easy sense. Okay. So nitrogen is N, oxygen is O, carbon is C. Those are great, easy, one letter. But obviously, we can't just use one letter for all of them because we only have 26 letters and we have 118 elements. So they also have, a lot of them have 2 letters. And the thing to remember when you're writing the symbols, it's really important that you write the first one as a capital and the second one small. Like if you looked here, if you got lazy and you write cobalt as capital C, capital O, that's not cobalt. That's carbon and oxygen together, carbon monoxide. So it's really important that you write them. Okay, so and a lot of these make sense too. Nickel, Ni, cobalt, Co. There's a lot of them. Argon, Ar. Those ones make sense. Okay, so if they're one letter or if they're two and it comes from their name, hey, no problem. But we got these goofy ones in here. Like, let me find a goofy one. Gold. Gold is Au. That makes no sense whatsoever, but actually it does. If you look at the elements that were kind of first discovered, they didn't speak English back in those days. This was Greek, Latin, that kind of stuff. So gold's name at the time it was discovered was Aurum. A-U-R-U-M. Well, it makes sense that its symbol would be A-U. And so when you see kind of goofy letters for them, you'll see that those were the elements that were kind of discovered first. Here's lead. Lead is Pb. Plumerium. Mercury, Hg. Okay. Let's see, where's another one? Potassium is another one. Potassium is K. Okay. So if it doesn't make sense, their symbol for their name, it's because at the time they were discovered, they didn't speak English. They spoke either Greek or Latin, and their name is from their Greek or Latin name. Okay, so, and those are the hardest ones to remember. Once you get them, though, it's a piece of cake. But most of them make sense. Aluminum is Al. Here's another one. Antimony is Sb. Old element, okay? Argon is Ar. Arsenic, As. Those all make sense. So you just got to kind of look at them and learn the elements, okay? And these are the ones I was talking about that came from their former name. These were old names, but, at the time, they weren't. Antimony, astibium, even copper. Copper, you think BCO, that's actually cobalt. But cuprum, aurum, ferrium, these are the ones that have weird, in our mind, a weird symbol to represent them, but really not so much because at the time they were discovered, this was what their name was. Okay, so now we're going to talk about the periodic table, and all the elements are placed in the periodic table by increasing atomic number. The first periodic table that was made was by a name of Dmitry Mendeleev. He was a Russian crazy guy, big old fancy beard. But he put all the elements in by their atomic weight. And if there was an element that wasn't discovered yet, he'd leave a space for it. And what was really cool, he'd say, okay, this element hasn't been discovered yet, but when they find it, this is going to be its characteristics. This is what it's going to look like. And he was spot on. So that was pretty cool. So his table really helped organize the elements. The problem was there was a couple spots where the atomic, excuse me, whoa, increasing atomic mass didn't work. There's a few spots where there's lighter elements on by the increasing number. So a guy by the name of Meyer said, hey, let's put them by increasing atomic number. And that's the number of protons. And once they put them in by that, the table worked perfect. So Mendeleev gets credit for it. Meyer gets credit for fixing it. Okay. When you look at a periodic table, when you go up and down the columns, those are called groups or families. And these guys have similar properties. That's why they call them families, because they react with the same things that look similar. And then you have, going across, you have periods. Now, just because they're next to each other in a period doesn't mean they have similar characteristics. So we have 18, if you count these, there's 10 in here. These are the transition. But we have 18 groups, 18 families, and then we have 7 periods, okay? Now, if you go by these groups, the A groups, so you'd have these two, we skip the transition and we go over here. These families have special names. The very first one is called the alkali metals, okay? These guys all have, and not hydrogen. Hydrogen should be separated here all by itself. Hydrogen is an element unique to hydrogen. There's no element like hydrogen. But all these elements, it would be lithium, sodium, potassium. These guys are all called alkali metals. These guys, it starts at boron and goes down, not boron, lithium, sorry. Lithium and down, not lithium. What is wrong with me? Oh, my brain's not working today. Anyway, these guys are the alkali earth metals. This is calcium and magnesium and things like that. And they have very similar characteristics. Then we go over here. These guys are all similar. They used to be called the boron family. And this would be the carbon family. And this would be the nitrogen family. And this would be the oxygen, because they're the first elements up here. They don't really have similar characteristics as these guys do. So they're kind of left out. But this group, 7A, this is fluorine, chlorine, bromine, iodine. These are called the halogens. And the halogens have similar characteristics, plus when they combine with a metal, they form a salt. And that's what halogen means, salt former. And then these guys right here are the noble gases. And the noble gases is a stuck-up group. They don't react with anything. And the reason for that, they're full. They don't have room to add anything. So, and this is helium and argon and krypton and things like that. Okay, so potassium is in the first group. The first group is alkali metal. Okay. Elements on the periodic table are placed in order of increasing, we just said that, atomic number. At first it was atomic mass, but now it's atomic number. Okay. The other thing with elements, all elements are of one of three kinds. They're either metals, metalloids, or non-metals. These aren't very good colors. Sorry about that, you guys. As you can see, most of the elements are metals. It's like 80-some%. Okay. All of these are metals. Hydrogen, being the rebel that it is, it hangs out with the metals. It's a non-metal. And all these green ones over here are non-metals. Okay. And then we have a group called the metalloids. And the metalloids are, there's this little step thing, and you can see. And there's not very many metalloids. Their characteristics are in between metals and non-metals, and they're found in between. So that's kind of cool. But you can see most of our elements are metals. Okay, so a metal is lustrous, which means it's shiny. Malleable, which means you can hammer it into sheets. It conducts heat and electricity, and that's what we really, really like metals for. That's our number one big purpose for them. We love that they do that. They're ductile, that you can stretch them into wires. Copper is really ductile, and that's what we make most of our electrical wiring out of, is copper, because we can stretch it and it doesn't break. They have high density. In other words, their particles are really close together. Again, makes them better conductors. And they have high melting point. So you can do a lot of things, put a lot of heat through them, and they won't melt. Okay? So those are the characteristics of metals. And again, most of our elements are metals. Non-metals is everything that's just opposite. They're dull. They're not shiny. They're brittle. They are poor conductors of heat and electricity. We actually call them insulators. Okay, usually we use a combination of a conductor and an insulator, like your metal wires, your electricity. There's also kind of a rubbery stuff on the outside to protect you so you don't, shock yourself. Well, that's made out of non-metals, okay? They're non-ductile, they have low density, and have low melting points. So they're just the opposite. Everything that a metal is, a non-metal isn't, okay? And then we have the lovely metalloids, and we love metalloids because if we didn't have metalloids right now, we would not be distance learning. Metalloids are the things that we make all our computer chips out of, those semiconductors. The thing with them is, like if you tried to make a computer chip out of a metal, the information would go through too fast and the computer couldn't grab it, the processor couldn't read it. But a metalloid allows stuff to go through it, but not nearly as fast. So we make all our computer chips out of metalloids, especially silicon and germanium. Those are the two big ones. And because of those, we have computers, we have cell phones, we have video games, all that fun stuff. And we wouldn't have any of that if we didn't have those metalloids. So even though there's not very many of them, we really like those guys, because just think how boring your life would be without all that fun technology. Okay, so a brittle sample, unknown, it's dull and brittle. Well, that's got to be a non-metal, right? The majority of elements are, we already talked about this, majority are metals. Okay, what is not a metalloid? You'd have to go back to that, and it would be aluminum. Aluminum is a metal. Okay, so when we talk about elements, most of them are found as compounds. Okay, the alkali metals, the alkali earth metals, they're way too reactive. You won't find pure calcium, you won't find pure sodium. They're always reacting with something. So a lot of times when we talk about elements, they're usually combined with something. You don't find a lot of. Now these guys, silver, gold, platinum, these are called the noble metals. These are why they're worth a lot of money. They're very unreactive metals, and there's not very many of those. Okay, and then the noble gases would be the other ones that don't react with anything. And I already talked about them a little bit. Those guys have a full energy level. They don't need to react with anybody. They're already calm. They're called inert. I call them stuck up because they don't react with anybody. Okay, so that's where we're going to end today. We're just about up with our 15 minutes. Make sure you do your assignment after this, and I will talk to you soon.